So I think last class, Vinay sir took a class on pigeonhole principle. Is that right?
Yes, sir.
Yeah. So we'll just continue with uh, some nice problems on the pigeonhole principle. And each of these problems, they're not just questions where you directly apply the pigeonhole principle. What's important is the takeaway that you get from the problem. It's how you apply the pigeonhole principle, right? It's different flavors of applying this, something like a theorem. And if you, as you start to observe and learn each of these different flavors, you'll be able to apply them in different problems as well, right? So try to analyze exactly what happened in each problem, like later after the class. And just uh, how I want the session to go isn't me just like giving a problem and then me solving it. I'll after each problem I'll give like about a few minutes time for you guys to try to solve it or think about it. And after that, even if you're not able to solve it, you can just tell me what you tried and what your ideas are, or what how you think the problem can be solved. Right after a few minutes of time. And you can raise hand. I'll just let you unmute, and you can convey your ideas, and then we'll discuss a solution, right? So does it sound good? And feel free to uh, don't be shy for unmuting, right? This is all just a learning experience. So if you unmute and you interact, you'll learn much more, right? That'll help you a lot. All right, so I've got problems of various difficulties. We'll start with something a little easier. Right. Um, so here we go. All right. So this is the first problem. So you have 10 numbers. When I say numbers, if I don't specify what's context, I usually just mean integers or positive integers. You can take it as whatever you want. To prove that if I give you some 10 random integers, irrespective of how I choose these 10 integers, you can always find two of them, a pair, such that their difference is a multiple of 9, right? So I'll give you a few minutes to think about it. If you solved it, or if you have any ideas of how to approach it, you can just raise your hand, and I'll open the stage to discussion like after a few minutes, right? So just think about it for now. All right. Yeah. Harini, you raise your hand.
Yes, sir. So should I explain it?
Yeah, sure.
Okay, sir. So if two numbers, their difference is divisible by 9, we can say that they're the same modulo 9. So, for example, modulo 9 means 12 is congruent to 3 mod 9, like that. So, we can take the worst case scenario. All the numbers are a different modulo 9. Now, there are only 9 modulo 9s. So, 0, 1, 2, 3, 4, 5, 6, 7, 8. So that means that the first 9 numbers out of the set of 10 numbers, they can all be different modulo 9s. But the 10th number has to be one of the 7. So by of the 9, so by pigeonhole principle, there are a pair of numbers whose difference is divisible by 9.
Exactly. Very nice. So when we talk about all these the modulo arithmetic, what we are doing is we are dividing the integers into what we call classes, right? So there is one class of integers 0, 9, 18, 27, 36. Okay, and minus 9 here, right? And all of these numbers are what you denote by, you say that they are 0 modulo 9. And there's nothing special about 9. You can do this for any positive integer, and you can do it for negative integers as well, right? Um, and here you have 1, 10, 19, 28, 37. Here you have minus 8, and so on. So these are all the integers that leave remainder 1 modulo 9. So these will be denoted by 1 bar. And all your classes can be represented as 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, 7 bar, and 8 bar, right? And you don't need 9 bar because 9 will belong to 0 bar again, right? So this is how modular arithmetic works. It's just a division of your integers into classes. And now what you're doing is you say, all right, every integer basically belongs in one of these 9 classes. These classes are basically like boxes, right? You have 9 boxes, and you have 10 integers. What that means is, by the pigeonhole principle, if there are more integers than boxes, 2 integers will have to go into the same box. Is that right? So if 2 integers belong to the same box, let's say that you have 2 integers a and b, both belonging to say 5 bar, right? Then a would be of some form, let's say 9 into x plus 5, something that leaves remainder 5. And similarly, b would be of some form 9 into y plus 5, something else that leaves remainder 5. And when you subtract them, what happens is that reminders cancel out, right? So you get 9 times x minus y. So basically, two numbers differ by a multiple of 9 only if the reminders are equal, right? So that's why we are looking at all of these classes, because by the pigeonhole principle, if you're able to find two numbers in the same class, then the difference is divisible by 9, right? So that's the approach that you think of when you try to approach this problem. So is this clear?
Yes, I had the same explanation.
Anyone had something different? I think someone raised their hand in the middle.
Yes, I had raised the hand, but I had the same explanation.
Oh, okay, yeah, sure. All right. We'll, we'll do another problem. Let's see. Okay. So prove that. Let me not write this. Okay. So you have 10 triangles, uh, none of which share vertices, right? So basically, you don't have any triangles like this and something like this, right? Which share a common vertex. There are no common vertices. Um, So the question is, what's the minimum number of points you must pick to guarantee picking all the vertices of at least one triangle?
Sir?
Yeah.
Sir, I think this is really similar to one problem which I've read, which states that we have uh, we have a certain number of socks which don't match each other. We don't. I mean, they are mixed up pairs, and we have a drawer in which we keep all those socks. So, what is the minimum number of socks we're supposed to take out of the drawer to get a proper pair of socks? Yeah, it's similar to that.
Yeah. In fact, if you think about it, it's almost the exact same problem. So all of these problems, which can be solved in one step using, or just like 2 or 3 steps using the pigeonhole principle, they all fall under one flavor. And if you think about it really carefully, any two of them are just similar. So it's nice that they're able to correlate between these problems. That's a really important skill that you should have. All right, I'll just wait for a few minutes. You can raise your hand if you have anything to convey, and I'll open the stage to discussion in just a few minutes. All right. Yeah. Yeah. Urvi?
Yes, so I think the answer should be 21.
Okay.
This is just because, like, suppose if we let the advisory pick the number of pick the vertices, and suppose like there are random triangles arranged, and so the advisory being wise, he'll firstly, for the first round, if we suppose, so he'll take one vertex of each of the triangles. Then for the second time, he'll take the second vertex of each of the triangles. Now for the third time, he definitely has to go for the third vertex. So even if we pick any of the rest vertices, we'll definitely have a triangle. So okay, in the first round we have 10, in the second again 10. So it should be, and one more when we pick, so 21. Right?
Nice. I actually like the language you use. So people
Yes,
usually call it the worst case
Vinay
scenario.
Sir usually uses this.
Yeah. Vinay sir has some really nice ways of explaining things. All right. So as she said, to simulate the worst case scenario, you can think of some adversary who's actually trying to hurt you as much as possible. And what you're saying is, you can hurt me all you like, but after a certain amount of time, that at this certain limit, I'm going to win. Like no matter how you try, right? Doesn't matter what you do, I'm going to win. So that's the kind of idea that you should have about the worst case scenario. So you just think, right? What all can I do to try to not pick all the vertices of a triangle? So you can just basically, it's like, you don't want to finish any triangle, but you want to pick as much as possible. So just almost finish every triangle, but don't finish it. So the best you can come to that is just picking two vertices from each triangle, right? And that means you're picking 2 times 10, that's 20 vertices. Which means if you're picking a 21st vertex, invariable of which triangle you choose, you have to pick a vertex of a vertex of a triangle where you've already picked 2 vertices, right? So that will be your third vertex, and that triangle will be fully picked, right? So does everybody understand the idea here?
Yes.
All right. That's what gives us one. Okay. So let me rewrite this problem. All right. So this is the question. So Vanessa basically has this camp, and he knows the number of students who are in the camp. This camp is just for students of high school, right, from classes 9 to 12. He knows the total number of participants who are there in this camp, and that's all he knows. And just knowing that information, he's able to claim that there must be either at least 9 students in class 9, or at least 10 in class 10, or at least 11 in class 11, or at least 12 in class 12. So how many students can there be in the camp? Like what is the possible number of students who are there in the camp?
And sir, it's only for 9, 10th, 11th, 12th?
Yeah, only for 9, 10, 11, 12. Yeah, only for high school students. So note that he only knows the number of, like, the total number of participants. That's all he knows, and he's able to claim without knowing any other statistics that this claim, at least 9 in class 9, or at least 10 in class 10, or 11 or 12, this claim is true, right? He's able to precisely claim that this is true. So how many students could there be in the camp? All right. So let's discuss. Has anyone solved the question? Okay. So then you can just tell me what ideas you have about. Yeah. Urvi.
Actually, I was trying to, so I am feeling like there should be some more information being given to Vinay sir, because like I have this idea particular, like suppose if I feel that he is being told that there is if there are students from 9th grade, then there are students from 10th, 11th and 12th grade. And if there are students from 10th grade, then there are students from 11th and 12th grade, but not 9th grade. So like I had this idea, and if we go according to this, like if this information is valid, in this question, then I feel 12 will be there. So I just thought about it. I am not so sure, like only based on the participants how he is able to analyze it.
Okay, so if you have 12 students, you could have 3 students from each class, right? You can have 3 students of class 9, 3 of class 10, 3 of class 11, and 3 of class 12. So then,
Sir, if they are having 48 students, then there will be 12 students in each class, and this will be valid.
okay, I mean, if you have 48 students, you can say that there must be 12 in each grade, right? And okay, so the idea that you implicitly used here is that you are imagining some adversary who is trying to split the number of students equally, right? Which is what we did in the previous problem. We split the number of maximum vertices you can choose without crossing the limit equally, and then we chose that extra vertex, and we said that you must choose at least that many vertices. But here, the worst case scenario need not be something where you choose an equal number of students from 9th, 10th, 11th, and 12th grade. In fact, it's not, right? So you have to be careful about what you think is the worst case scenario because you have to prove that it is. Right?
I think it is 42.
42. Okay, why?
Yeah. In the total number of students which can maximum, I took the number of students in each grade with Vinay math so that there should at least be. So there are 9 students in 9th grade, 10 students in 10th grade, 11 students in 11th grade, and 12 students in 12th grade. I added them up. I got 42.
Yeah.
So in 42, there must be at least so when you add any number of students, you will get at least 12, at least 9 ninth. Say that there are only 9th and 10th grade students. So even if there is only one 9th grade, the rest should be 10th, and there will surely be more than 10 10th graders. Or say there are 9th, 10th, and 11th. So if there is 1 9th and 1 10th also, there will be about 40 11th graders. And if there are 12, if the students are there from all 4 classes, there will be at least 39 12th graders from previous examples. But on taking the worst case, on dividing it by 4, we get it to be 39. Okay, sorry. It should be 9, 10, 11, and 12 would be the 4 numbers which you would get, and they will be there will surely be at least 12. Even if there are only 9 12 graders, the others would be crossing their minimum limit. So it has to be minimum 42 students.
Yeah. So yeah, the idea is right, but there's a small detail that must be revised in the solution.
Can I?
The idea is perfect. Oh, once again, before you say something, the way you think about these problems, again, the problem is, first of all, you don't need to worry about there being no 9th graders or no 10th graders or no 11th or no 12th, because then you can just say that the number of students in 9th grade is 0, right? That's mathematically perfectly valid. So you don't need to worry about that is some sort of special case. And the second thing is, you have to think really carefully about what should be the worst case. First of all, in the previous question, why was the worst case? Why did the worst case have an equal number of vertices in all the triangles? Because none of these triangles are special, right? There's nothing that differentiates these triangles, and hence there was a lot of symmetry in the problem. Here, that's not the case, because here it's okay to have, let's say, 10 9th graders. If there are 10 9th graders, the answer is right. But if there are 10 11th graders, that doesn't prove Vinay sir right yet, because it's not the same. He's not made the same claim for 9th grade and 11th grade. So there is a lack of symmetry here, and you have to be really careful about what you call the worst case. Now, the solution is almost right, but there's a small detail that you have to take care of, right? And the way you take care of this detail is by answering precisely what's the worst case. When you answer that, the answer or like the answer to the question automatically follows. Yeah. So who asked whether they can go?
Yeah, I
Yeah.
had like a similar idea, but I got multiple answers as my as the result, because it says how many students can there be.
Yes.
So
Yes.
the problem says there must be at least 9 students in 9th grade, 10 in 10th grade, 11 in 11th grade, or 12th in 12th grade, which means it can either one, and that too, we want to look at the worst case. So we have to take the least number of students in each grade. So then the first case is that only one of them takes one of them is true. They can't be more than one of them at the same time. So because uh, only one among the four claims can apply because of the or, uh, we have to just add everything because we have to look at the worst case scenario. So I also got 42. But earlier I had considered taking cases like only one takes place, only two take place, only three take place, and all the four take place. But because there's an or, you can only limit yourself to one condition at a time, and the least number of students in that condition. So it's 9 plus 10 plus 11 plus 12.
All right. So okay. So here's a problem with
I
trying
have
to.
a different idea. Found out
I
what-
had a doubt actually.
I'll just address this solution and I'll come to you guys.
I have a different idea for the solution.
Yeah. I'll open it up to discussion. I'll just address what happened in the solution. So the problem is, okay, there's a mistake which I'm not directly able to identify, but the problem with the approach is it's extremely hard to work with or conditions in some cases, because you have to say what happens if this happens, what happens if this happens, what happens if this happens, right? And you have to take care of all these several possibilities. But there's a very neat way in which you can combine all of them, and that's looking at it as an and. It's much easier to look at ands because it's all packaged into one. This must happen, and this must happen, and this must happen, right? They have to all happen together in one case, right? And saying not of A or B or C or D, right, is the same as saying not A and not B and not C and not D. Do you get what I mean? If I
Yeah,
say
so we
I
have
have
to take the cases approach, like only.
exactly.
Okay.
So
So
if I
you
say
can
I
you can get multiple answers like only 9, or 9 plus 10, or 9 plus 10 plus 11, and 9 plus
no.
10 plus
See, yeah, that's the thing. You don't need to work with all of these separate cases because okay, if I say something like I have a bat or I have a ball, right? The opposite would be I do not have a bat and I do not have a ball, and this negation statement allows you to work with the worst case in a very nice way. So, who was the first person who asked me they want to share an idea? Like after Anushka?
Anushka.
Oh, okay. The second Anushka. Yes.
Yeah. So since you talked about negations here, so I got one more idea. So first, what I thought that we could do, like we have an or statement. So even if we have 15, so if the answer could be 15. So if we have 15 students, just taking Kirti's idea that we have one student in ninth, and then we get 10 students in 10. So that is fulfilled. Then if the students is 9th, 10th, 11th, then also if we have one student in ninth, one student in 10th, we still have 12 students in 11th grade. So that is also fulfilled. And if we have students from ninth, 10th, 11th, and 12th, we will have one student in ninth, one student in 10th, one in 11th, and then we still have 12 in 12th grade. So 15 could be a possible answer. And now, since you talked about negations, we could take that there are we don't have A students in ninth grade. We have or we can say we have less than 9 students in ninth grade, less than 10 students in 10th grade, less than 11 students in 11th grade, and less than 12 students in 12th grade. So I think that would mean the worst case scenario as 8 plus 9 plus 10 plus 11, and that becomes 38.
All right. So your first solution, there was a mistake in the part where you assume. All right. So you say, let's say there are 9th, 10th, and 11th grade students. You say that okay, there is one student of 9th grade, one student of 10th grade, and 11 students of 11th grade. But why can there be 3 students of 9th grade, 3 students of 10th grade, and 11 students of 11th grade? Sorry, let's say 10 students of 10th grade, right? In that case, it wouldn't work, right? You can't assume anything about the number of students there are in any grade. You can only derive it from, you have to basically know that, okay, yeah, it's definitely possible that this claim is true. If with 15 students, right? It's also possible if there are only 9 students because all of them can be 9th grade. The question isn't when this could be true. The question is when this must be true if for a certain total number of participants, right? Irregardless of how many students there are of how many, whichever grade, if you know that the total number of students is this, then one of these statements must be true. And this where you come to your second idea. This is hitting the bullseye, right? So you took the negation of this statement. What is the worst case possible? Well, I'm going to take almost. I'm going to make every statement of yours almost true, but just not true, right? We're just taking 8 students in 9th grade, right? Just like the maximum I can take without taking an extra student. The idea of this problem is that if there are a lot, if say there are a billion students, right? Obviously, there are going to be a lot of students of some grade, right? And that's the idea you should use. There is some limit after which you can guarantee this to be true. And the question is, what is that limit? So to answer that, try to answer what is the limit where this is false, the worst case scenario. And that is extremely easy to answer. This is what you've answered here, right? So the worst case scenario is where I take 8 students from 9th grade, 9 students from 10th grade, 10 from 11th grade, and 11 from 12th grade, right? And that comes up to 38 students. So with 38 students, there is a possibility that Vinay sir is wrong about his statement, right? And it's also true for any number below 38 because you can just take away students from this count. But what about more than 38? Is the statement always true for more than 38?
I think yes.
You think yes? Uh,
I think so, no, because if we have like less than 9 students in the 9th grade, and if we continue to increase the numbers maybe in the 11th and 12th grade, then there might be some cases where the condition is not satisfied for 9th or 10th grade, or like vice versa.
I have a doubt. Is it like there should be 10, like 9 students in 9th grade and 10 students in 10th grade always, or can it be like 8 in 9th, and then like if only one criteria is satisfied, is it okay, or like
yeah,
all four?
you just need one to get satisfied.
Oh, okay, then 38. Yeah.
Note that at least is the most important word here. There need not be exactly 9, right?
Yeah.
Um,
No, mine's like from every grade you need 9, 10, and 12, or can I just satisfy like one statement, like
no,
only 9?
just one. If even one of them is satisfied, then it's satisfied, right? So again, or is also
then
important.
39.
Yeah, 39. Yeah. So that is the answer is right. 39 is right because note that we haven't assumed anything else. All we said is if this is not true, what's the maximum number of students there can be? It's 38, right? Because we just took the negation of what Vinay sir said, and the maximum number of students there can be in the case where Vinay sir is not right is 38. So for 39 and above, Vinay sir cannot be false, but that means Vinay sir is what he said is true, right? Are you able to get the idea? So 38 is the maximum number of students you can have with Vinay sir being false, which means for 39 and above, Vinay sir cannot be false, so that means he must be true. So you get this idea of negation?
Yes, sir.
So this is something you've been implicitly using while doing worst case analysis in pigeonhole principle problems. But you had to get a really strong foothold on this idea of worst case scenarios, because sometimes it's really hard to analyze all of these or statements. Right? Let's say that prove it that if I have 40 students, I can do this or this or this. Sometimes it's easier to say, if I cannot do this or this or this, I can have at most 39 students or whatever. So that if I have 40 students or above, this must be true. So this is actually a technique in mathematics called using the contrapositive, right? So if you have something like A implies B, right? Then not B implies not A. So it's just basic logic, right? So let's say that there can only be rainbows if it rains, right? So rainbow implies rain, right? Because if I see a rainbow, that means it must have rain. Okay, I don't know whether that's exactly true, but let's assume that to be true. On the other hand, if it rains, there need not be a rainbow, right? So rainbow implies rain. On the other hand, if I know it did not rain, then there cannot be a rainbow, because for a rainbow, you must have rain, right? Which is the exact idea we used here. So if Vinay sir is false, then there can be at most 38 students. So the opposite of having at most 38 students is having more than 38 students, which is like 39 or above. So if you have 39 or above, then Vinay sir cannot be false, so he must be true. So the answer is 39 or above, right? Did you all understand the solution?
Sir?
Yeah.
I had a doubt in the interpretation of the problem. So the statement that he only sees the total number of participants. So does it mean he does not know the grades of the students? Like
yeah, he doesn't. So all he sees is, all right, he looks at the sheet and let's say the number was, let's say 43, right? So he looks at the sheet and he says, okay, there are 43 students, and that's all he knows, right? He knows there are 43 students, and he knows that all of them are from high school. So he looks at it and he says, okay, so by the pigeonhole principle, this statement must be true. Right?
Okay, sir. Thank you.
Yeah.
Even I had a doubt in the interpretation. Like, even if we consider 39, I think he should be known of the information that there are students of all the grades. Like, even if we consider of high school students, there can be students only of 10th, 11th, and 12th. So, is it like, shouldn't it be necessary that he should be told that there are students of all the 4 grades?
No, and the reason is, let's say that there are no students from 9th grade, right? Then you can just say that there are 0 students from 9th grade. It doesn't make a difference. Pigeonhole principle works just as well with using 0 along with the positive integers, because you're not, it doesn't contribute to anything. So you can say there are 0 students from 9th grade, 9 students from 10th grade, 10 students from 11th grade, and 43 minus how much ever I've taken in 12th grade, right? In fact, if you have 0 students from 9th grade, that's only going to be inefficient if you're trying to if you're trying to prove him wrong. Because you can't just fill in those spots with 8 students in 9th grade, right? There's no requirement for specially analyzing the case where they have 0 students. Grammatically, it makes a difference, right? There are no students from 9th grade. We're talking about 0 students. But mathematically, no, it doesn't make any difference. Right? Do you get the idea?
Yeah, okay.
So, is everyone comfortable with the ideas used in the problem?
Yes, sir.
Sir, I did not still understand the connection between the grade of the student and the number of students. Like, how did he actually predict the minimum number of students in each grade if he is not aware of the grade of the students?
Okay, so let's say that I have okay, so let's say that I have a box with red marbles and blue marbles, right? And only red, only blue, and you know it, I know it, and I show it to you. You don't look, and you start picking marbles. So can you, if you pick 3 marbles, can you assure me that there are 2 marbles of the same color?
Yes.
Yes, if all the marbles are of the same color, then yes.
No, I mean, okay, so you take 3 marbles out of, and every marble is either red or blue, right? So can you assure me that 2 marbles have the same color?
Yes.
No, but they might be red or white, right? You can't assure that both of them will
Yeah,
be
yeah,
of the same color.
exactly, right? There might be 2 of red or there might be 2 of blue. You don't know which. Exactly, right? And that's the same
Yes.
thing here. Vanessa says there might be at least 9 students of 10th grade, right? That's why he uses the statement or, right? At least 9 in 10th grade, or at least 10 in 10th grade, or 11 in 11th grade, or 12 in 12th grade. Only one of them needs to be true for Vanessa to be right. Not all of them.
Okay.
Yeah. So make sure that before you try the problem, you have to fully understand what they're trying to convey, because sometimes if you misunderstand the problem, then you'll be working on something that's probably false, right? And no way you can prove something that's false. All right, we'll go to the next problem. Okay, this is a very nice problem. All right, so this is the question. You have a party of 100 people. So it's just a gathering, and as a greeting people, they might shake hands, they might not, right? And what I want you to prove is that no matter what happens there, right, there exists like 2 people who shook an equal number of hands. So let's say that in the whole party, um, A shook hands with only X and Y, and B shook hands with only C and D, right? Then A and B both shook 2 hands, and hence they shook an equal number of hands, right? Or if A and B both didn't shake hands with anyone, and they only shook hands with like among themselves. So let's say A shook B's hand and B shook A's hand, but they didn't shake hands with anyone else. Even then, they shook an equal number of hands. They shook 1 hand each. Or if they didn't shake hands at all, they shook 0 hands each, which is still equal, right? So I want you to show that no matter what happens in this party of 100 people, if every pair either shake hands once or they don't shake hands, then you can find 2 people out of these 100 who shook an equal number of hands. I'm not saying it's true for any 2. You can find 2 such people.
It is not the case that everyone at least shakes hands once.
Yeah, that's all good. All right. Yeah, Bhagyashree.
Yeah, sir.
Yeah, you raised your hand. Did you have anything to say?
No, sir, I have answer.
Oh, okay. You had an answer. All right. I'll just wait for 1 more minute and then I'll ask you to explain, right?
Yes, sir.
Okay.
Sir, I wanted to ask, can we try proving this by induction, or do we have to stick to the pigeonhole principle?
You can use whatever you want, right?
Okay,
If,
sir.
yeah, I'm not going to be a school teacher who says you have to do it using this step only, right? You can do it however you want. But okay, if you have an alternate solution, then I'd be interested to know what you did. So that'd be something that we all can benefit from. All right, yeah, Bhagyashree.
Yes, sir. I'm just theoretically answer the question. Means let us take two people from 100 people, and there remains 90 people to shake hand with one people, and another one people will sorry, and one people shake hand with 49 people, and another one people also shake hand with another 49 people. They both are shake their hand with all the 90 people, but there at least exist 49 people who shake hand with both two people. So with induction, we also take we take induction hypothesis. Let us take two people from 100 people to second with 90 people. Let us base case one.
Hello.
Hello.
One second. Could you mute a second? Yeah. Okay. It got too loud in the background. But I wasn't quite able to understand what you were trying to convey. It was just a little too noisy. Maybe you can enter.
I'm so sorry, sir.
Yeah, no, it's not a problem at all. Maybe you can enter your ideas to me in the chat. That would be fine. Right? Meanwhile, yeah, does anyone else want to convey? Even if you do not have the whole solution, it's fine, right? You can just uh, tell me how you think you can approach this problem, what ideas you have. That's the important part here. It's not important to solve the problem. Nobody cares that there are two people in a party of 100 people who shook an equal number of hands. That's not the takeaway here. The takeaway is the ideas that you have, the way you approach this problem. Yeah, so Arya?
Yes, sir. So I'm not like very confident about the solution, but if we take k number of people who have shook hands and 100 minus k people who haven't shook hands, or we can also increase this to the possibility that k number of people have shook the hands x number of times. Well, 100 minus k have shook y number of times, or they haven't at all. So in that case, k and 100 minus k will always be even, because for shaking hands you need two people. So the k and 100 minus k will always be a multiple of 2.
What are k and 100 minus k?
So in this case, we can take k as a number of people who have actually shook hands, while 100 minus k haven't.
Yeah.
So here, for the base case, we can't take k is equal to 1, because if the person has shook hand, then there has to be another person who has shook hand with him or her. So there has to be like at least two people who have shook hands. So if we take k as equal to 2, then we get 100 minus k as equal to 98. So
Yeah.
100 minus k people haven't shook hands at all, which means they have 0 handshakes. So in this case, we get that there exist 2 people with equal number of handshakes because
Yes.
98 people haven't shaken at all. So this in this way we can increase k to 4, where 100 minus k becomes 96. Even there we can use the same argument till the point we get k as 98 and 100 minus k as 2.
By the way, k need not be even. Just to illustrate, you could have 3 people, Alice, Bob, and Charlie, each of whom shake hands with one another, right? So k need not be even. But okay, I get your point. So k up till 99. K up till okay, so k up till 98. But what do you do when there's when k is 99 or 100?
Sir, I have to work on it.
Okay, yeah, this is a good idea, right? So starting, I mean, okay, so you won't require probably all of these ideas, but the motivation behind how you're thinking about this problem is the way you should approach it. Okay, so Vaishnavi asks, if there are n people and n minus 1 possibilities, number of people each person can shake hands with. The number of people each person can shake hands with. Okay, great. Then at least 2 people have shook hands with an equal amount of people. Is this assumption correct? It's not only correct, it's the best way you should go about this problem. So that's a great idea. I'll just explain what Vaishnavi said. Or Vaishnavi, do you want to unmute and explain that? Yeah, Vaishnavi.
So, sir, I was saying
Okay, I think.
that
Yeah, I think there's some audio problem from this. Is that the case? Yeah, hello. Are you able to hear me? Yeah, I think your voice is breaking. All right. Yeah, no worries. I'll just explain what you put in chat.
sir, I was saying that let's suppose.
Yeah.
Okay, sir. Thank you, sir.
Yeah, sure. All right. So what she's saying is, if you have, let's say, 10 people, right? Let's say I'm just taking 10 people, and let's say that every person shook hands either 5 times or 6 times or 7 times. Okay, let me say there are 4 people. And if I know that every person shook hands 5 times, 6 times, or 7 times, can you say that there are 2 people who shook hands an equal number of times? So you have 4 people in some really large group. It's not just the 4. So you have 4 people in a really large group, and every one of these 4 people shook hands 5 times, 6 times, or 7 times. Can you say that there are 2 people among these 4 who shook hands an equal number of times?
Yeah.
Yes, sir.
Why?
We applied this in the first problem also.
Exactly. Yeah. This is the pigeonhole principle. And her wonderful idea is to try to apply this in our problem as well, right? If you have a set of possible number of handshakes that a person could have done, and the number of people is more than that, by the pigeonhole principle, there would be 2 people invariably who shook an equal number of hands. Are you able to understand this idea? All right, so let me just read Bhageshri's chats for a second. So let us take 2 people from 100 people, shake hands with the remaining 98, and 1 person shake hands with 49, and 1 person shake hands with another 49. Okay, again, see, like when you start assuming these things, you start assuming what is the worst case scenario. And the worst case scenario need not always be people shaking an equal number of hands. This is all in a case where you want symmetry or you have symmetry. But here we're looking for asymmetry. Again, we're looking for people who have, if you're trying to simulate the worst case, you're trying to make people not shake an equal number of hands. You see what I'm saying? So that idea won't, it won't give you a proof. All right, we'll just proceed with what Vaishnavi said. So is everyone able to understand the idea that she proposed?
Sir, so
Yeah,
isn't my answer correct?
Yeah, it's not exactly correct because if you have
Yeah, sir. I am just answering the question theoretically. We also get the answer by induction.
no, I mean, okay, so the problem is you can uh, again, if you induct, what are you inducting on? The so if you're going by induction, what's the way you approach this problem? Because if you're trying to induct on the total number of people, uh, and I'm trying to remove people so that I can make the set of people smaller and then try to apply induction. Let's say I was among these 100 people and I got removed. I might have shaken hands with some one person, and the number of hands that they shook after I'm removed will decrease by one. But there might be another person who I did not shake hands with, and when I'm removed, the number of handshakes they have might be unchanged. So the number of handshakes that these two people did might not be equal, but they can become equal, right? So induction won't give you the answer either if you're not being careful about all these changes. The problem with the first solutions is that again you're trying to analyze the worst case scenario, but this isn't exactly the worst case scenario, right? We are assuming a lot of things. They're saying that this is the worst case scenario, such as if there are two people shaking hands at 98, then one shakes 49 and the other shakes 49. All of these assumptions, they need not be true, right? Or you might not even be able to divide the party into two sets of
No,
people who
sir.
shake hands among each.
So both two people shake hand with all of 98 people. But there are at least exist 49 people who shake hand with both two people. I'm just trying to say that.
So you take. Oh, okay. So you assume that there are two people who shake hands with 98 people. Is that right?
Yes, sir. And there exist at least 49 people who shake hand with both two people. And 49, 49, and 98.
Okay. So you can say that. Wait, if you're saying that both people shook hands with the remaining 98 people, then one person would have shaken hands with 98 and another person also would have shaken hands with 98, right? I mean, if you're assuming that two people shook hands with 98 people, then it automatically means that the problem is solved.
So I didn't understand.
But isn't this only true when all of them shakes hand with all the others?
What?
Because for what by pigeonhole principle, there can be n minus one shake hands, and there are n people.
Oh yeah, I'll come to that idea later. So I'll talk about that later. Once again, I'll just address Bhagesh's proposed solution. So yeah, if you're taking two people who shook hands with the remaining 98, are you saying that both of them shook 98 hands, like together or individually?
So individually, the
So this person shook 98 hands and another person shook 98 hands.
yeah.
So if you assume this, then your problem is already solved because you can just take these two people. They shook an equal number of hands.
So,
But you might not always be able to find two such people.
so what are you saying?
Yeah. So if two such people exist, yeah, the statement is true. But what if two such people don't exist? Then what do you do? Then you can always assure that two such people exist, right?
Yeah, two people from around 100 people, and two people second with another 90 people.
Yeah, but this you might not be able to find these two people who shake hands with 98, right? Maybe in the party, like people shook hands with a very less number of people, and nobody shook 98 hands, right? So, again, there's a lot of technical details that must be filled in before this can become a proof. All right, I'll just go.
Yes, sir.
Yeah. So I'll go ahead with what Vaishnavi said. So just to make sure that everyone understood what Vaishnavi said, her proposed solution is that you have n people. If you have n people, and you have a set of possible number of handshakes that they could have done. Let's say they could have shaken like say 3 hands or 5 hands or 7 hands, and this set has size n minus 1. Then by pigeonhole principle, there must be 2 people who shook an equal number of hands. So now, yeah.
I have a doubt, but this can be true only when all of them shook hands with all the shook hands. If say that one of them didn't shake their hands,
Yes.
so it won't be true, right? There will be.
So if in your set of the number of handshakes also includes 0, right? A person shook with 0 hands. Sorry, a person shook 0 hands, not shook with 0 hands. So again, there is nothing that special about 0 here in this case, right? You can just say that they shook 0 hands, right? So that's a perfectly valid thing to say. So the question is, what is this set? What is the set of handshakes that a person could, number of handshakes that a person could have done? Could a person have shaken -3 hands? No, right? Could a person have shaken 0 hands?
Yes.
Yes.
What about pi hands or 3/4 hands? Right? Or 9 3/4 hands? Right? No, right? Only an integer number of hands. Could a person have shaken 1,000 hands?
Not within the standard people.
No.
If he repeats, then with the same people, then it is possible. But
There is no repetition, right? The problem says
yes.
he shakes, every person shakes one hand or no hand at all. So then, okay, so now can you tell me what is the minimum number of hands that a person could have shaken? The minimum is
99.
the minimum is 99.
0.
So 0. Everyone must have shaken at least 0 hands.
Yeah.
Right?
Yeah,
What about
because
the maximum? The maximum.
you
nine.
shake everybody's hand.
Everyone 99
Exactly.
hands.
Yeah.
Exactly. 99. Because this is not something that people usually do. Right? Shake hands with themselves. So the set of possible number of handshakes that you could have done is numbers from 0 to 99. And obviously everything in between is possible as well. So it's 0, 1, 2, so on to 99. And you have 100 people. What's the number of elements in the set?
100 elements,
100.
including 0.
100 elements. It falls just short of uptime pigeonhole principle. If it was a set of 99 elements, then it's say, oh, by pigeonhole principle, there must be 2 people who've shaken an equal number of hands. But now I have a set of 100 elements. It just doesn't work because of this one small extra element, right? But here's the thing: there's a small catch.
I think I figured it out.
Yeah.
Maybe the person who. So let's say that when this person does not shake hands, no one would have shaken hands with this person. So there can't be any 99 option at all.
Exactly. Right?
It will come down to 98.
Yes, that's the solution. So here's the catch. You have 100 people and you have 100 possibilities for the number of handshakes, but not all of these 100 can come true simultaneously, right? That's if there was an adversary, right? And he was just assigning numbers to these people from 0 to 99. That is what is happening, right? You have 100 people and you have 100, you're assigning a number to each of them. Obviously not every assignment is possible, but okay, let's say that you're assigning numbers to these people as the number of handshakes that they have done. If you have 100 people and 100 handshakes, the only case where no 2 people have shaken the same number of hands is where every person shakes a different number of hands. So there must be one person who shakes 0 hands, one person with one hand, one person two handshakes, one with three handshakes, so on till one with 99 handshakes. That is the worst case, right? But the problem is, now you ask, okay, this is the worst case. If I'm assigning 100 numbers to 100 people, then two people need not have the same like the same number. But is this assignment possible? This is the only assignment that will uh, uh, that will make sure that all people have a distinct number of handshakes. But is this assignment even possible? Is it possible that a person shook 0 hands and then a person shook one hand, another person shook one hand, a person shook 2 hands, so on till the 100th person shook 99 hands? Is this even possible? Right? And what Kirti said is, no, it's not possible, because if there's a person who shook 0 hands and if there's a person who shook 99 hands, right? Let me call them A and let me call this person B. A shook hands with 0 people. What does that mean? A shook hands with nobody, right? On the other hand, you have B shook hands with 99 people, which means B shook hands with everyone. If A shook hands with nobody, then A couldn't have shaken hands with B. But if B shook hands with everyone, B must have shaken hands with A. And you're led to this contradiction, right? It's not possible for two such people to simultaneously exist, right? So you have removed this worst case. That is the only case where you can have your 100 numbers in your set. So once you've eliminated this case, then there can only be a set of at most 99 number of handshakes that a person could have done. And now you can apply the pigeonhole principle and say, all right, so now by the pigeonhole principle, there are two people who have shaken an equal number of hands. All right, so does anyone have a doubt about how the solution worked? Again, if you didn't understand any part, just feel free to unmute and ask me, and I can just repeat the explanation for that part.
So how we can solve this problem?
Yeah, so, okay, so I think I might have not explained. Okay, so I think you will be able to understand the full solution. I'll just try to repeat the outline again, but if you're not able to get the intuition, then I think you should just check the recording. So I'll just try to explain the intuition behind it. So it's a combination of two ideas. First, if you have n people and the total number of the number of handshakes that any person could have done is only one of n minus 1 numbers, right? So let's say there are 4 people and every person shook hands with, let's say, either 3, 4 or 5 people. Then by the pigeonhole principle, there must be 2 people who shook an equal number of hands, right?
Yeah.
So the idea is, all right, so if there are 100 people, can I say that there are at most 99 possible number of handshakes that a person could have done? So the number of handshakes that any person could have done must be a number from 0 to 99, right?
This means one people shake hand with other 99 people.
No, not one person with the other 99. So it's like some person who shook hands 0 times, or some person who shook hands 1 time or 2 times or whatever, right? What are all the possibilities? The possibilities are only 0, 1, 2, 3, so on to 99.
Yeah,
Then you say, all right, how many numbers are there in the set? There are 100 numbers. But not all of these 100 are possible. It's not possible that one person shook 0 hands and another person shook 99 hands, right? Because then 0 handshakes means this person shook hands with nobody. But 99 handshakes means the other person shook hands with everyone else. So you will see that it will imply that these two people both shook hands and did not shake hands. It's not possible that both are true, right? Only one of those two statements can be true. Either they shook hands or they did not shake hands. So you cannot have both 0 and 99. You can have only one of them. So you can have one of 0 and 99, and you can have the other 98 numbers. So the maximum number of possible handshakes that an individual could have done is only like at most 99. And then you see the pigeonhole principle. You see that 2 people must have shaken an equal number of hands. Again, if the idea isn't fully clear, I suggest that you go through this again and again and again, right? Until that idea finally, clicks in your mind. It's completely all right if you're not able to fully assimilate the idea. If you think about it a lot, you'll eventually understand what the idea behind the proof is. All right.
Yes, sir.
Yeah. So, very cool job. See, that's a great group effort, right? So you have individual ideas and you just combine them. It's okay to not have a full solution. It's the ideas that matter. You can just put them together and you can get a great full solution. All right. So is it fine if I do one last problem? Because I think that will be a helpful problem. It's actually a homework problem that Vinay sir gave, which will allow you to solve another problem. So is it fine if I take one more problem?
Yeah, you're sure.
Sure.
Yes.
Okay. Cool. So that's a problem. I don't think I need to write it. Okay, but I'll just repeat the problem in case anyone has not already taken it. So the problem is if you color all the points on a plane using blue and red, is it possible to always find an equilateral triangle whose vertices are of the same color?
Yeah, we've done this.
Yeah,
Yes, I wrote this.
Yeah, Vinay sir wrote this, but he didn't solve it, right? So we'll try solving the problem.
Actually, we solved it like in a peer discussion group. Like I think Betsy, we did it.
Yeah, I think.
Yeah, we did it.
All right, so wait. How many people already know the solution to this problem? Wait, if people in bad C didn't, yeah. Oh, okay. Looks like quite a few of you know the solution. All right, no problem. Okay. So do people know the solution to the other homework problem that you gave about coloring? You color a plane with 18 colors.
Yeah.
Yes, sir. We've also
We
discussed
finished that
that.
also. In that also.
Yeah, even the hexagon.
Okay, you finished both problems.
Yeah.
Okay, that is that's troublesome because there are people who do not know the solution too. All right, would you mind if I did one of those again?
Yeah.
You know,
It's fine.
Sure, sir.
yeah. All right, maybe it will be a good second summary. So I'll take the equilateral triangle problem because it's a little easier. So if you color up all the points on a plane, either blue or red, right? So literally every point, I mean every point on the plane, all the infinitely many points in the plane is either blue or red. Then is it possible to always find an equilateral triangle? So like I'll select some random 3 points on a plane which form an equilateral triangle. Can I assure that I can pick 3 such points which form an equilateral triangle, such that no matter what is the coloring, I can find a red, red, red. All of these 3 vertices being red, or all of them being blue. Right? So again, people who already know the solution, you don't need to raise their hand or give spoilers, because let's just keep it new for the people who haven't solved the problem yet. All right. So I don't think we have much time, so I'll just discuss this problem, and then we'll because you'll be able to apply a similar idea in another problem, which is actually another homework problem that Vinay sir gave. So usually when you're working with these problems, it's hard to work with the whole plane. Right? You can't even imagine a whole plane fully colored with blue and red. Right? It's not physically possible. So what you try to do when you're approaching these kind of problems, if your idea is to use the pigeonhole principle, then your idea must be to try and, or I mean, just any coloring problem, try and find repeating patterns, because when you find these repeating patterns, you will be able to find a lot of you'll be able to find a dense set from which you can choose nicely. So let's say that I have a pack of marbles, each of which are one of the 7 colors of the rainbow, right? If I want to ensure that I pick 2 marbles of the same color, would I pick a small number of marbles or a large number of marbles? Forget the exact number. So if I want to ensure that I pick 2 marbles of the same color, should I pick a small number of marbles or a large number of marbles? Large, yeah. Right? Because if I pick a small number of marbles, it hurts my chances. And that's the exact intuition behind these problems. If we're able to find these large network of equilateral triangles which share all these vertices, which kind of communicate information within each other, then you will be able to sort of construct a proof through this network, right? So if I want a lot of equilateral triangles, sharing vertices nicely, what kind of network should I use? What kind of pattern do I use? If you just think about a lot of equilateral triangles placed efficiently. You want to pack a lot of equilateral triangles together. How would you do it? Exactly. Yes, a hexagonal pattern, right? It's basically the beehive pattern where you have all these hexagons which are tessellating with one another, and you can fill the whole plane using hexagonal tessellations, right? Because it just fits 360 degrees perfectly. It fills full angle perfectly. And what you can do is you can divide every hexagon into 6 equilateral triangles, right? And then you get a lot of equilateral triangles. So let me just draw a few more equilateral triangles. Right. Here. Here. Let me draw this one as well. Alright, now we have a large number of interconnected equilateral triangles. The reason we want this is because if you color a vertex of one triangle in some color, it applies to all triangles which contain that vertex as well. It kind of shares information with the other triangles, and it will let you, prove things. It will give you stronger information, right? So let's start out. Let's assume that I want to do the contrary, right? Which is color the plane in some way. Here I'm just coloring all these. Okay, this should be just one point. Right? So I'm just trying to color all of these points, right? All of these, what I would call lattice points, because these equilateral triangles, when they tessellate, they form what we call as a lattice, right? It's a triangular lattice. The squares tessellate forms a square lattice, which is what you're used to. It's a coordinate grid, right? And you have hexagonal lattices and so on, right? And what I'm going to do is I'm going to try to color all of these lattice points blue or red, such that I cannot find an equilateral triangle which has all 3 vertices of the same color. And because you have so many equilateral triangles here, this is the same.
Sir, I have a doubt.
Yeah.
So, when we mean coloring half the plane, do you mean like counting the total number of triangles and coloring half the number, or do you mean like splitting it in two and coloring half that in?
You color the whole plane. That's not half the plane.
Okay.
Sorry if I wasn't clear. Alright, so for once, let's actually go with red and blue, right? People just they circle the vertex and then they write R or B. It's all in black. So now let's say that I want to color this lattice such that I do not have I do not have an equilateral triangle with all 3 vertices of the same color. So let me start. For starters, I can just assume some vertex and assume that it's blue. Right? There's nothing special about red or blue. It's just one color or the other. So let me start with the blue vertex, right? So now, can I color both of these vertices blue?
No,
No.
Why not?
you'll form an equilateral triangle.
We'll form an
Exactly.
equilateral triangle.
So one of them has to be red. Can I color? Oh, okay, so let's say that I'm going around the hexagon, trying to maximize the number of blues I color around. So let's say I'm doing something like blue, red, and then blue.
So you can do it alternatively.
Yeah. Blue, red, and then blue here, and red here. Right? So
Already formed an equilateral triangle.
where? Right? None of these equilateral triangles, none of these equilateral triangles.
But all the three blue on the
Yeah, the three
edges and
blues
all
and
the
the
three
red.
reds.
Yeah.
Exactly. Right? There are these bigger equilateral triangles as well, which is this is what's so special about all of these networks. You find these small equilateral triangles and these big equilateral triangles. They're just completely swamped with equilateral triangles. It's like this crowded group of equilateral triangles, which are assembled in some place, and it gives you a lot of restrictions. Right, that's the strength of these networks, which is why you should try to work with them. Right, so again, as you said, you cannot have this as well, because then these three form an equilateral triangle. These three form an equilateral triangle, and these three form an equilateral triangle. Right. So now, all right, you say, okay, so at least, so can I color all of the points around the blue vertex, right?
No.
Yeah, because again, you can find the same sort of triangle, right?
Yes.
So there must be at least one blue vertex around it. And let's say that point is here, right? Again, there's nothing special about any of the points around it, because it's just an infinite lattice, right? Now, can I say that the remaining are red, all the three remaining? Sorry, all the five remaining.
No.
No. Why not?
Because again there will be so you when you color all four of them red.
All five, yeah.
Yeah. So there is again an larger equilateral triangle.
Yeah, here.
Yeah,
Right?
yeah.
So there must be one of those 3 points, one of these 3 points must be blue as well. They can all be red. Which
No, but
point must be
actually
blue
for
though?
one hexagon you can color it off like using different colors. Then when you're gonna move on to the next one, that's when you'll get stuck. Actually, like if the advisory is like playing a smart move, they'll be able to like successfully complete one hexagon, but then they won't
Exactly.
get to go after that.
Yeah, one hexagon is possible. But then this is the strength of unity, right? All of these equilateral triangles assemble together and they say, no, you can't do this. So, all right. One of these 3 points that I've circled in red, not all of them can be red, because then they'd form an equilateral triangle with monochromatic vertices. So then one of them must be blue. But which one? Can all of them? Can I just choose any of them to be the blue one?
No, you can put the red one to play like the.
I mean, all 3 of them are red right now.
The
So
straight
can I make
line.
this? Can I make this blue?
No, the straight line can be blue, like the last
Yeah.
point of it.
Yeah. So this can be blue. That'll form an equilateral triangle. This can be blue. Again, that'll form an equilateral triangle. So it has to be this point where all of these blue points form a line.
Sir?
Yeah.
So I think I found a formation that doesn't form any equilateral triangles.
Okay. I'll just finish it and then wait, in this lattice, right?
Yeah.
All right. So we'll come to that. All right. So now let's move. So if there is one hexagon, then you can just go on coloring the remaining, the 4 vertices, right? And you'd have no equilateral triangles.
Exactly, you can just complete it.
Exactly. So now we had to go to another hexagon. You had to look around another point. So let's say we're looking around this point here. right? So again, can all the 5 points around it be red? Why not? Because because these 3 points will form an equilateral triangle as well, right?
Yeah.
So what you have to do is take one of them to be blue. But once again, this can be blue because this would be an equilateral triangle. This can be blue because this will form an equilateral triangle. So this has to be blue. Is that clear? So this has to be blue. Is that okay with everyone?
Yes.
But by the same argument, this would have to be blue, right? Because neither this nor this can be blue. And then this would have to be blue. And this whole line that all of these collinear points form, that would entirely have to be a blue line.
Yes.
Not all the in-between points which are not inside the lattice. Like this point also has a color in the plane, but we're not considering those points. We're only considering coloring the points which form the lattice. Right? We're saying you don't need to color the whole plane, just color these points and I'll find a monochromatic triangle. That's enough for me. Right? We're proving a much stronger statement. Alright, so you have this whole line formed by all of these points. All of those points in the line are blue. Is this clear?
Yes, sir, and we can also say that all the points in the line above and below it will be red.
Exactly. Right? And why is that?
So that so no equilateral triangle will be formed with 3 points of the same color. So
Yes.
if we have say this point as red, then we can't make any of this one red or this one red. So these would this one, the above two ones red. So which means that this would have to become red. Similarly, we can go on saying that this one, and this one would also have to be red.
Okay. I'm not sure whether I exactly got what you're saying, but that statement can be proved a little easier, right? What happens if that is blue instead? Can you find an equilateral triangle with blue? So if this was, okay, so let's say this was some vertex on this line. So let's say this vertex was blue. Is that a problem?
Yes, sir, there is a
Yes,
problem.
the smaller equilateral triangle is getting formed.
Exactly. So this would have to be red, right? And this point has to be red as well, but the same argument.
Yes,
and
the
this
entire
point,
line would be red.
Exactly. So this entire line would be red. But what about the next line?
It has to be blue.
Yes,
Right?
so the line above it has to have all
No,
points
it's
red.
And that will form an equilateral triangle.
Yeah. So you
a
can just
bigger
go,
one.
It has to be from an equilateral triangle.
Yeah. So you can just go like saying all the, so you have red line, blue line, red line, blue line, red line, blue line, so on. All of the lattice points are colored, and yeah.
But then there's again a problem, because if this is blue, then we form this equilateral triangle.
Exactly, but you don't have another option. If you have red also, then you'll form it. So basically, whatever you color there, you'll form an equilateral.
Exactly. Right? You're just trying to be the adversary, right? And you're not trying to just be the adversary, you're trying to be the adversary's brain. You're saying, all right, how all can I completely, spoil if I want an equilateral triangle, then my adversary is like, no, I'm not going to give him that. And I'm going to try everything I can to prevent that from happening. So the adversary is trying every single case and extinguishes all the cases, right? You have to be sure they don't assume anything. If you assume anything, then also assume also solve the problem of what happens when that's not true, right? It's fine to assume something as long as you also deal with the case where it's not true, right? But once you deal with every case possible, and what you want to do is not possible in any of those cases, it cannot be true in whole, right? So it's just a beautiful problem. You see all these equilateral triangles coming together in very nice and different ways, right? And they just group together and make sure that you cannot find a coloring where you do not have a triangle with vertices of the same color. So is this idea clear? Yeah, Anushka, you want to provide a counter example?
Yeah, so can I annotate?
Yeah, sure.
Yeah, so it was something like this. So I took 1 second. Yeah, so I took red and green. So
Okay.
I
Yeah, sure.
let this be red.
Yeah.
I'll just color them in the order I've already finished. And this is green. Yeah.
Isn't there an equilateral triangle having red?
Yeah, there's already an equilateral triangle.
Oh, yeah.
The
Okay.
bigger one.
Okay. I got it. All right. Thank you.
Yeah. No problem. So that was amazing, right? It was a very healthy group discussion. I thoroughly enjoyed that. And I want you to apply the same idea. Okay, obviously it's not going to be this, just replace all the triangles with squares and just go boom, the same solution. No, it's not going to be that. You have to apply more ideas as well. But you can, it's the same starting point, right? Same starting motivation, which is you group all these squares together and try working with a square lattice. So that's how I want you to approach this problem, where you color a plane with 18 colors. Prove that no matter how you color them, how you color the plane, there always exists a rectangle with vertices of the same color. So I color, I go color red, blue, indigo, green, and another 14 colors which I do not know the names of. And you have to show that no matter how I color the plane, I can always find 4 points which have the same color and which form a rectangle. So instead of, okay, so before I had equilateral triangle, and I looked at equilateral triangles, kind of tessellating. If I want to look at rectangles, a lot of rectangles, what do I go for?
It would be the same case as the squares.
Exactly, yes. So you just look at a square grid, right? In fact, you can look at a rectangular grid, but okay, for convenience, let's just talk about square grids. A square grid is bunched with rectangles. So if you have a square grid, let me just, you have all these tiny squares which are also rectangles, but then you have rectangles of this sort, right? And you have rectangles of this sort. In fact, this whole grid is a rectangle, and so on. So just take an infinite grid, right? How you look at the lattice in your graph sheets, right? Just look at that grid and try to work with the same thing. But okay, don't start coloring with 18 colors and see how far you can go without getting a rectangle. That will take you an eternity, right? But try to use the same starting idea. That is, look at the lattice, the lattice points on this grid, and then just work with the points on this grid and see whether you can. It's possible to have a rectangle. Sorry, to have no rectangle of with vertices of all the same color. Right here, you can just brute force it and look at all the cases and solve. You have to be a little more clever.
Okay, sir.
Yeah, and there you'll be able to apply the pigeonhole principle very nicely. Yeah, that's right. So yeah, this is a great problem you can try. It combines a lot of very nice ideas. This is the starting idea, and you can try, you should definitely try this, of course, right? As well as the other homework problem. And okay, you have 2 problems. I have some other problems that no, actually, never mind. Yeah, I think these 2 problems are good to try. The 2 problems that this is one homework problem that when I gave, the other one is prove that in a given set of 5 non-negative integers, there always exists 3 of
We
them
did also
with some
that. We also
divisible
did
by
that.
3.
Yeah.
We also
Oh,
did that.
he did that in class.
I mean,
Yes.
we did. We didn't do it in class.
Okay, so yeah, if you've not solved it yet, then that's also an easier problem to solve, right? That would be something that you can try first before trying this problem. Yeah. So
Hello?
that's
Hello, sir?
yeah.
So, but I didn't understand that question. Five numbers and.
Oh yeah, I'll repeat the question. You can just take it down, or let me
Yes,
just
sir.
type it.
I know the answer. I know the question, but I didn't understand the answer. We discussed in another class, but I don't know the
Oh,
answer
okay.
how to solve.
Hi, I'm not discussing the answer now. I haven't discussed it yet.
Yes.
And I don't think I think there are other people in your batch as well who haven't discussed the answer with anyone else. So you can just try to give it a go by yourself. Uh, and if you're not able to solve, then you can ask the sir for the solution, or you can even healthier is actually to ask one of your peers for the solution, right? You should. Do you guys have a group where you interact with one another? I don't mean just a WhatsApp group where the admin says you have class and so. Here's the meeting link, and you all say okay, okay, okay. I mean a group where you all talk with one another. No. So if you don't, then I highly advise you people to form a group and actually interact among yourself. Uh, I don't mean with the faculty, right? It's a really healthy habit to collaborate, because when you collaborate, you start to learn how the other person is thinking as well, and it's a symbiotic process, right? All of you can grow into better mathematicians if you start working together. So that's something I would highly advise. Other than that, yeah, if you do not know the solution yet, you can just try the problem, or if you're not able to get the solution even after trying a lot, just ask one of your peers here to give you an idea.
So how can I ask? I am a journalist student and living in hostel, and I have no WhatsApp group.
Oh, okay. So what? Hello.
Yeah, can I say something?
Yeah.
Yeah. So do you guys want a peer group discussion again on any Sunday or tomorrow as well? If you guys want a peer group discussion, we can have
Yeah,
a meeting tomorrow.
that would be amazing. Like I think that these people should have sessions where it's just them without the
Yeah,
faculty.
right. Only for the peers, only for the students.
Yes.
The last time we did.
So would that be okay for all of you?
Yes, it sounds like a good idea.
How many students want? The maximum students want, then then I will start meeting tomorrow.
The thing is that we don't have any problems from the camp, but we can do any new problems.
Yeah, sure. You can discuss whatever you want.
Yeah.
Yeah, we can.
Yeah, sure. Then at what time? The same timing as today?
Can we do it in the morning?
Hello.
Yeah, say.
Not yesterday. Can we make meeting on Monday or in school time?
Actually, there are annual exams coming on Monday, so there are few people who I think who may not be able to join.
Yeah, actually, the Sunday will be the okay, no?
Tomorrow's fine.
I was asking that is it possible to have meeting from 10?
10 in the morning.
Yes, ma'am.
Yesterday 10 to 12 or 10 to 11. I can.
Okay, in the morning. Do you want? Oh, okay. Last time actually we did it in morning, right?
Yes.
Yes.
Then we will be able to attend the meeting.
Yeah. So, will everyone okay with the morning timing?
Yes. Yeah, in between 10 to 12.
Okay, then we will do it from 11 to 12. Okay, for all.
Yeah, 11 to
10 to 11 we can.
10 to 11?
Okay, it's okay. 11 to 12.
Yeah, right. Okay. So tomorrow, 11 to 12, right?
Okay, ma'am.
Yeah. Okay.
Yeah.
Thank you so
All
much,
right.
ma'am.
I
Yeah,
hope you all have fun. Do you want me to send some problems, or you guys will find problems of your own?
Sure, sir. Do send.
Sir, could you send some
If
problem?
you could send a couple of problems, it would be easier for us to make more problems of that sort.
Okay, sure. That would actually be really awesome, right? You will all prepare like one problem each as well, and I'll send a few problems. I'll probably send something like I'll send like 2 easy problems, 2 medium difficulty, and 2 hard problems. And I think that would be perfect. So you can just try problems, whichever difficulty you want. Right? Form groups, discuss. Right? Don't be a lone wolf. Right? This is an activity where you have to interact so that you can grow up. Right? It's fine if you're not able to contribute anything. Try to contribute your ideas, and even if they're not whole solutions. Wait, are you speaking to Mish, Nadmila? Oh, okay, I think she's just relaxing. Yeah. All right. So
Thank you, sir.
even if you're not able to contribute anything, yeah, just try to learn from others. It's a great experience. I hope you have a lot of fun. Right? And thank you for staying for the extra time. Right? I'm so sorry about that. All right. Bye.
Bye, sir.
Yeah, thank you, Haran. Thank you all. Bye.
I'll send it to I'll send the problems to Neha.
Yes, you can.
Yeah. Okay. Thank you.
Thank you, sir. Thank you, sir.
Thank you.
Thank you.